Hi there, Mr. Sutton here, bringing you the AB Calculus 616 homework solutions on free response area and volume. For this no calculator free response, we're given the region R as bounded by 2 radical x and the horizontal line y equals 6 up here. We want to find the area of R for this first part of the problem. So I'm just going to be doing an integral from left to right of top minus bottom. So that's going to be the integral from 0 to 9. They gave us this point here. That was nice of them. And I'm going to be doing top minus bottom, so that's going to be 6 minus 2 radical x, or 2 times x to the 1/2 power, dx. Rewrite it just to make it a little easier to integrate by hand. So now my antiderivative, I'm going to have 6x, and then this, let's see, this bumps up to 3/2, multiplying by 2/3. I've got 4/3 x to the 3/2, all of that evaluated from 0 to 9. So I've got all of this with 9 plugged in, and I'm going to rewrite this stuff right here as, let's see, 4/3 times, this is the square root of 9 cubed. And then I'm subtracting all of this stuff with 0 plugged in. And now evaluating that, I actually don't have to go any further since I've got all constants. But if you did want to simplify this, you'll notice that everything in this second bracket is going to get zeroed out. So it's really this first bracket that gives us our true values here. We've got 54. And then, let's see, square root of 9 is 3, cubed is 27, 4/3 times 27, well, 27 divided by 3 is 9, times 4 is 36. So this is 54 minus 36, which is 18. For this part, they want us to write but not evaluate an integral that gives us the volume of the solid generated when R is revolved around the horizontal line y equals 7. I'm going to start by drawing that line just so I have a good visual of what's going on. So that's somewhere up here. We don't have to be too precise here. What we do need to notice is that we have a space between the axis of revolution and the bounded region here. That means when I'm integrating my area of my cross sections for this solid, I'm going to have to use washers rather than discs because I've got this hollowed out part here. So I'm going to write as my area cross section formula a sub 1 of x equals pi times big R squared minus little r squared. And I'm saying a sub 1 because I'm going to be writing another area cross section formula on the next part. I don't want to mix it up with this one here. So plugging in some things for this. Big radius, that's the distance from this horizontal line to the further away part of the bounded region. So this is going to be 7 minus 2 radical x, the whole quantity squared. And we'll still have a pi outside there. So pi, and now inside a big parentheses, 7 minus 2 radical x squared. Now for the little radius, that's the distance from my axis of revolution to the closer part of the bounded region. So this is going to be just 7 minus 6 that we're squaring and subtracting from everything. Now I need my integral, so I'm going to say my volume equals the integral from still 0 to 9, same limits of integration, but now we're just going to be integrating a sub 1 of x dx. And since we don't actually have to evaluate it, and we told them what a sub 1 of x actually is, we are done with this part. For this last part of the problem, they're telling us region R is the base of a solid, and for each y between 0 and 6, cross-sections taken perpendicular to the y-axis are rectangles, with a height 3 times the length of the base. They want us to write but not evaluate an integral for finding volume of the solid. So we've got rectangular cross-sections perpendicular to the y-axis. In order to do anything on this, we're going to have to rewrite this y function here in terms of y itself. So I'm going to have basically have x equals something with a y in it. So I'm just going to isolate x in this function. I'm going to divide y by 2, so we have y over 2, and then I'll square both sides to get x by itself. So I'm going to rewrite this as x equals y over 2, the whole thing squared, which I'm not going to bother simplifying because at the end of the day we don't actually have to evaluate this integral. Now what am I going to do this? Well, I need to get an area of my cross sections first of all. Since my cross sections are rectangles, I'm going to start with a of y equals base times height. But now I don't want to have this height sticking around. I want to express everything in terms of the base because the base is dependent on this y function that I just wrote here. So they told me that my height was 3 times the length of the base. So this is just b times 3b, which is 3b squared. And now what is the actual base defined in terms of y? Well, the base is the distance from the axis of revolution here, or the boundary here, to this other boundary. So this is just a horizontal distance given by this x equals y over 2 squared function. So I'm just going to write in here 3 times y over 2 squared, and then squared that whole thing. So a lot of squaring going on. All right, now we need the actual integral. So my integral, I'm going to be integrating now from bottom to top because I have y-axis integration going on. So now my integral is going to be from 0 to 6. And for that, I'm just going to do this a sub 2 of y dy function that I just defined. And again, since I don't have to evaluate this, this problem is finished. For this calculator-based free response problem, R is a region in the first quadrant enclosed by the y-axis and the graphs of y equals 1 minus x cubed, this top one here, and sine of x squared, which they also labeled in the diagram. That was nice of them to do that. For the first thing we're doing on this problem, we want to find the area of this R here. Since this is a calculator-based problem, I'm going to define these two functions so I don't have to keep rewriting them as f and g. So I'll let f of x be the top one, 1 minus x cubed, and g of x will be my sine of x squared. All right, so to get this area, if I integrate from left to right using vertical distance strips, I'm only going to have a single top and bottom function, so it makes sense to do this. So let me first figure out where these two functions are crossing, and then I can just integrate from 0 to whatever this x value is. I'll call it p after I find it. So let me go to Desmos and clear out anything that's already in there. And now let me enter my two functions in there. So we have f of x equals 1 minus x cubed, and g of x equals, what was that again? That was the sine of x squared. Sine of x squared. Okay. And clearly this looks a little bit different from what I see up here, but I just need to zoom in ever so much, and there is the region that they've highlighted for us in their diagram. So we want to figure out where these two things are crossing. If I click on one of them and click on this gray dot right here, it looks like 0.764 and some change. You know, I'm just going to select this and copy this, and I'm going to call this point P. And now I can just keep going back to it. So I see that these intersect at, and I'm going to call it P on my work as well, so P equals 0.7650. And now I just need to do the integral from 0 to P of, and now I just need to do a top function minus bottom function, or I could put it all in an absolute value and not worry about it. But since I'm already thinking in this vein here, let me just do f of x minus g of x for that, dx. And now we go straight to the calculator, and let's see what this comes out to. Let me just move so I can see. So we've got integral, int, from 0 to p, and that'll be f of x minus g of x, close that, dx, comes out to about 0.534. For part B on this problem, they're telling us that a horizontal line, y equals k, is drawn through the point where the graphs that they gave up here intersect. So we have a horizontal line going through this point right here. They want us to find k and then determine if this line divides R into two equal sized regions here, two equal areas, and then show the work. All right, so let's find k. Since that's just the point where these cross, we really just need the y value where they cross. We already got the x value. So just going back to Desmos and clicking on one of these and clicking on this crossing point, that is the point. Well, the y value here is 0.552 and some change. I'm going to select that, and I don't need this integral anymore, but I am going to let k equal that number that I just found. And I'll write that down here as well. So f of x equals g of x at y equals k equals 0.5524. Now I've got this stored. So what I'm going to do is I'm just going to find the area between the between k and the bottom function, and then I'll find the area between the top function and k. from 0 to p, and we'll see if those areas are the same. So let me do the bottom area first. Both of these are going to have limits from 0 to p. We're still going to the x value p here. Since I'm doing the bottom function, I need to do the line k minus this g of x function down here. And let me go to Desmos and see what that actually comes out to. So I've got integral from 0 to p of parentheses k minus g of x dx, and that comes out to about 0.277 if I round that off. And let me do the top area now. That's also going to be from 0 to p. But now we're going to have f of x minus k. Now f of x is the top function. And let me go back to Desmos and enter that in. Let me just recycle this integral here. So we're going to do f of x minus k. And that comes out to about 0.257. Now this does not match the bottom area. Since those are not equal, we conclude that y equals k does not divide R into two equal regions. For the final part of this problem, they want the volume of the solid generated when R is revolved around the line y equals -3. Let me just sketch that line. I don't really know what the scale on the y-axis is, but it's somewhere down here, not drawn to scale at all. The key, though, is that there is a gap between the bounded region and the line of revolution here. That means that for my area formula, I'm going to have to use washers rather than disks. So for my area, I'm going to write pi times big R squared minus little r squared. A of x equals that. Big R is going to be the distance from the further away part of the bounded region, which was our f of x function. The distance from that to this line y equals -3. So we're going to have f of x minus -3, or plus 3 as it were. And then little r is the distance of this inner part of the bounded region, which was our g of x function. So that'll be g of x plus 3, quantity squared, all being subtracted. So at some point I'm going to put this area formula in my calculator, and then I'm going to integrate that from 0 to p. So 0 to p integral of a of x dx. Let's go to the calculator and actually do that. So let me get rid of this integral here. Let me write down, and I don't need k actually while I'm at it here, but let me write down a of x equals pi, parentheses, and what's in this parentheses? There's a lot going on here, so I'm going to set up my structure first. So let me close that parentheses. In here now, let me put a parentheses that I'm squaring, and I'm going to subtract another squared parentheses. And now in each of these squared parentheses, I've got f of x plus 3 and g of x plus 3. So f of x plus 3, and going back down here, we've got g of x plus 3. And now that I've got that all set up, let me come down and do my integral from 0 to p of a of x dx. Comes out to about 11.841. So that's our volume. For this no calculator free response problem, we're given the f function, this polynomial, and this trig function for the g function. And just looking at our graph here, because they did give us a graph, it looks like g is going to be the top function. This looks like cosine here. And the bottom function, f of x, is a piece of a polynomial. All right, it's actually part of a parabola here. So first task is to find the area of R. And again, we can't use a calculator, as nice as it would be. So my setup here, they at least gave me the limits of integration. I've got an integral from 0 to 2 of, I'm going to do top minus bottom. So that's going to be this cosine function minus this other function. And I'm going to write everything out because I'm going to have to do this by hand. So 4 cosine 1/4 pi x minus parentheses 2x squared minus 6x plus 4. Whole bunch of things to take antiderivatives of, and I actually need, I think, another parentheses in there. There we go. Okay, so going left to right, doing this by hand. So this would be, let's see, this would normally be 4 sine of all this stuff, but I have to divide by the inner tail here. So that means I'm actually multiplying by 4 and dividing by pi. So that's going to be 16 over pi sine of 1/4 pi x. So that's a fun one to take there. And then for the rest of these, keep in mind as I do these that everything is being negated inside this parentheses. So this bumps up to an exponent of 3. Dividing by that, I've got negative 2/3 x cubed. For this next one, this is going to become a positive. Positive, let's see, divide by 2, so 3x squared. And this is going to be now negative 4x. All of this evaluated from 0 to 2. So I've got all of this stuff with 2 plugged in, minus all of this stuff with 0 plugged in. Now, if I plug in 0, before I actually bother writing all of that out, I mean, clearly anything with an x right here, these polynomial terms, is going to get zeroed out. How about this trig function? Well, if I've got 0, that zeroes out everything inside sine. The sine of 0 is 0. So really, I'm not going to bother writing out all these things with 0 plugged in. I'm just going to write out minus 0 because that's what it is. But I do need to evaluate the rest of this. Although, actually, now that I think about it, this is a free response problem, and these are all constants. So, yeah, you could actually just like stop here and get on with the rest of your life. But if you wanted to simplify, let's see what it would come out to. So inside the sine function, this is really 1/2 pi, or pi over 2. Sine of that is 1, and that's just 1 times 16 over pi, so just 16 over pi for that whole first term. For this next one, this is 2/3 times 8, so that's 16/3 we're subtracting. For the next one, this is 3 times 4, so 12 that we're adding, minus 8. And then if you wanted to combine terms a little bit more, 12 minus 8 is 4. 4 plus negative 16/3, that's negative 16/3 plus 12/3, so that's minus 4/3. 16 over pi is still hanging around, and honestly, this is as good as it gets, unless you want to try merging this into one big fraction. For this next part of the problem, they want us to write but not evaluate an integral that gives us the volume of a solid of R being revolved around the horizontal line y equals 4. So I'm going to draw that on here so I have a visual of what I'm doing. That's up here. If I'm revolving around this line, that means I have a space between my axis of revolution and bounded region. So I'm going to use washers for this. I'm going to say a of x equals pi times big R squared minus little r squared. And I'm actually going to write a sub 1 of x because I'm going to do another area cross-section formula in part C, and I don't want to mix it up with this one. All right, so I need to actually define big R and little r. Big R, the big radius anyway, is going to be the distance between my axis of revolution and the further away bounding function. So that's going to be 4 minus whatever this bottom function was. That was actually the f function. So 4 minus f, and I'm squaring that. And I still have this pi hanging out outside here. Next, for my little r, that's going to be 4 minus the closer function, so 4 minus g of x that I'm squaring and subtracting. For the integral now, I'm going to say the volume equals the integral from 0 to 2 of, well, just a sub 1 of x dx. I'm not going to rewrite all this because I already told them what it was. On this problem, we're told that region R is the base of a solid, and each section perpendicular to the x-axis is a square. Write but don't evaluate something for the volume of the solid. So let me get my cross-section area formula now. I'm going to write a sub 2 of x equals s squared. And then for these squares that are going perpendicular to the x-axis, I basically define the base of each of these squares, one of the sides, need to do top minus bottom. So they already named the functions for me. I'm just going to write g of x minus f of x for one of these sides. So then I've got g of x minus f of x squared. Now I just need to write the integral now that I have the area formula. So I'm going to have volume equaling integral from 0 to 2 still. That hasn't changed. And now just a sub 2 of x dx.